In a previous video about how if we have an amine in the presence of an alkyl halide, the nitrogen is going to keep removing hydrogens until you end up with this tertiary ammonium halide, tertiary alkyl ammonium ion. Well, this in general is undesirable, but there is a situation where we want this to happen, and this is called the Hoffman Elimination. So to undergo the Hoffman Elimination, we need a very specific set of reaction conditions, but if we can get to these conditions, it's actually pretty great. We'll see why. It allows us to really easily form, if we need to, terminal alkenes. So one of the compounds we need is N,N-trimethylamine. So we have 3 CH groups attached to the nitrogen. And the reason we need this is we need the lone pairs. Now, the other thing we need is an alkyl halide that contains iodine. And there's additional stipulation that the carbon next to that carbon, the one that carbon next to the carbon that contains the iodine, needs to contain a hydrogen. So we need something of the form CiR2CHR2. I know this is a very esoteric, very specific reaction, but we do need it, and we'll see why in just a minute. So what will happen is this nitrogen will displace the iodine. And we will end up with the trialkyl ammonium complex, as well as iodine as the counter ion. Now, this on its own is not particularly useful, but what we're going to do next is we're going to add a silver 1 oxide catalyst. Well, not a catalyst, it's going to react. But what this is going to do is it's going to do 2 things. One, it's going to eliminate the amine group. And subsequently, it's also going to eliminate the hydrogen off of that carbon. Now, this elimination is going to be done anti. So the stereochemistry we finish up with is one where we have to rotate these 2 R groups so that this hydrogen is on the opposite side of the bond. It's anti the ammonium complex. And when we're done with this, we will finish with an alkene. Now, I haven't specified what these R groups are here on this carbon, but preferably these are hydrogens because it will make it a lot easier for the ammonium to substitute. So if these end up being 2 H's, we will end up with a terminal alkene. So this is the advantage of the Hoffman elimination. We are using a catalyzed reaction that will basically remove an iota group and give us a double bond on the very end of a carbon chain, particularly if we're working with a CH2 group or a primary iodo alkyl halide. Now again, go back to your notes on how to do alkenes. You'll see that actually elimination from the terminal groups is pretty hard to do. The big reason is that even if you try to drive it using an E2 mechanism, it's going to be prohibitively slow, and if you try to do it by E1, you're probably going to end up with rearrangement. So this use of an amine to promote the elimination is the advantage of the Hoffman reaction. Basically, it allows us easily and synthetically to create a terminal alkene.